Hi, I'm Paul from Test Data Services, and this video summary is going through X-Ray in detail. So I'm going to show you how to get this service map up and then how to be able to interpret it. The wonderful thing about this service map is the color coding. So if you notice here, this little purple, this is what we want to actually target in this video. It's to do with throttling of DynamoDB calls. So I'm going to show you a load test with 14,000 concurrent users. I've got some sampling set up. I've got some special scripts set up. I've got some even a AWS X-Ray group for monitoring set up, so that we can actually have a pretty good deep dive into root cause analysis of performance issues and stability issues using X-Ray. So if I've set up chapters in this video, so you can skip forward if you don't want to look at the way I've set up the test or compare it with previous test runs. But I hope you find this interesting because the whole learning process for me for X-Ray has been really quite wonderful. So to start with, I've got ready here a load test. I'll just push this aside for now. So the load test, I'm going to start it up first. I'm going to start up 72 load generators for this test. And while that's starting up, I'm going to show you what I've changed in the script since last time. So in the script, I used to have 3 lines at the beginning that hard coded the client ID, the base64 authorization code I use for the back channel OpenID Connect calls. And for the OpenID Connect stuff, go and have a look at the other video. I've got a link a card up in the top right hand corner for that. And then a subscription ID. Now, when I use just one client ID, I've got in my code a hot segment, or hot partition rather, for OpenID Connect. And I want to show that, but I want to show it a bit less brutally than with just one. So I've set this test up to have 10 different OpenID Connect client IDs, but I've made it so that one of them occurs 55% of the time. So let's have a look at that. Double click on parameters, and these are my 10 IDs. And if I just show you with an external editor, I've got this, the 10, and I've repeated that first one 10 times. That means it's represented in this parameter file 11 times out of 20, which is 55%. I've also set the script up. Let's go back to main. Set the script up so that in the default headers for this this load testing script, instead of having a normal user agent, I've actually put the client ID, I've embedded the client ID in the agent. This means in X-Ray we'll be able to see if this 55% distribution of client IDs is correct, and we should even see that the errors for throttling are happening disproportionately to this particular client ID. So I think that's quite a neat little thing for us to do. So that's the script. Now that we've launched those load generators, let's just check and see how that's going. Instances, refresh. We've got 72. It looks like they're good, which is great. Let's have a look and see if we can connect to them. Connect. Hopefully we have 72 connections. Connecting. One more. Last one. All 72 connected. That didn't take very long. Okay, I'm pushing the start button. So this test is going to run with 3 groups that are repeated multiple times. One of them is collecting metrics as per a previous video, so I can actually look at how many concurrent Lambdas are running and what my responses are for various Lambda calls, and what my metrics are for DynamoDB and some other things. So I can actually see them as the test is progressing, remembering that all those stats are coming back 1 minute delayed because of the granularity on CloudWatch. So that is running nicely. I also need to show you what I've done in the Lambda code itself to enable X-ray monitoring. So this is one of the Lambda functions. All I had to do was go down and tick this box to allow active tracing. I did a similar box ticking exercise for API gateway, and to make it so that we get visibility into the calls that are made from within this Lambda function, I added in, let's just make this a bit bigger, I added in these two lines here, which specifies the X-ray code, which is necessary so that we can actually see the calls to, say, DynamoDB or whatever else it calls. And I put in here a maximum retries of 5. So I'm expecting in this test run to actually have throttling occurring with DynamoDB, and I want to actually let it do multiple retries. The retries are exponential, so what that will mean is the response times will take longer and longer in a throttle situation. But that means we'll be able to actually see the response times start to blow out before we start to get throttle messages. So that's the authorize call. That's the DynamoDB that I've got in there. And let's have a look now at X-Ray. So we've now got 3,500 users running. Response times are flat. Everything's looking pretty good. So let's now do relative time and look at the last minute and refresh. So this is now a service map of X-Ray for the last minute. And we can see there should be no errors in here. I can make it a bit bigger. And the way this works is each of the incoming requests. So the nice thing about service X-Ray, the X-Ray service, is that the service map shows us an end user perspective. So in the same way with load testing, we want to simulate things from the end user. X-Ray has an end user perspective as well. So in this case, this is the OpenID Connect token call, which in this case goes to the API gateway stage for that call, and it's going right down here to a token call, and that's calling Lambda to actually fire off this request. Now that Lambda request is touching a DynamoDB table called person, OIDC scope, tokens, AMR, and tags. But if I was to look at something like tokens, I can now click on the tokens little circle, and whenever I click on one, I get a blue line here, and that's telling me that's what I'm focusing on. That's giving me information over here as well. But if I click on this, I can see that I've got two functions interacting with this table. I've got the token call and the authorize call, which is great to know. Now over this side, I've got a response time distribution for this minute of requests. And we can see that we've got most of our requests are happening at around the 100 millisecond mark, and the average, you've got 0 there and 20 milliseconds, so around the 11 millisecond response time, and we can see here 11 milliseconds. I forgot to show you sampling before. Let's go back and show you sampling. So I've got a default group. Now in the default group, I've set a reservoir size of 1 transaction per second or request per second. So that means I'm getting 1 even if I'm just doing some shakeout testing. But I've got a fixed rate of 1.66%. Now I've played with bigger numbers, 5 and 10%, but I actually like doing 1.66% because that's a 60th of 100. What that means is if I go back to my service map, all of these numbers in here, if I refresh, will tell me how many transactions per minute the samples are being collected. But if I have 8,000 per minute, then that's actually per second in actual underlying transactions. So this is telling me how many samples have been collected in a minute. But what it really means is we've got 8,400 requests per second, and I'm only sampling 1.6% of those. Now we're at 9.6 thousand requests per second going into the tokens table, for example. So that we've got a bit of yellow here, which is good to know. It would be good to see what that is. We can click over here on errors whenever we get that and analyze traces, and we can actually look at what those errors are. We've got a time display over here. Basically it tells us we've had a few at close to 11:22 UTC. We can scroll down and we can see that 3 of the errors were for one client ID and one was for a different client ID. And we can actually have a look at what those errors are. We can have a bit of a trace. And in this case, we can see that we've got a remote fault caused by validation exception. So I've got some sort of a problem with my code that happens occasionally. We'll dig into that separately. Let's go back to the service map. And now the default service map for, let's make it last minute. The default service map is everything that's coming in, which is quite useful. But I've got another service map which I'd set up earlier, a group, and that's going to show me any throttling. So the purpose of this test is to start to see throttling and help us to zoom in on that throttling and then have a detailed look at it. We haven't got any at the moment. Let's go back to the default one. And in the default map, I'll make it bigger when it comes up. We've got these few errors, and you can see we're doing quite a few transactions here. So, 11,000 transactions per second is actually quite good. I know this is per minute, but like I said, we're doing 1/60th of the requests are being sampled. Let's have a look at our load test now. We've still got flat response time. Over here, we've got 9,500 users running. And we're tracking with this line how many concurrent Lambdas in the previous minute. We're at 420. So if our response times stay flat, our Lambdas are consistently performing. What that means is that we'll continue with this same trajectory. So we're at now 9,800 users running. We're doing 6,600 requests per second. Now hits per second, which actually means that it's including redirects, so that the second request after a redirect. If we look at transactions per second, which are mostly OpenID Connect calls, we're now at 5,900 calls per second. And what we want to watch is when we get to around the 13,000 users, we're going to start to see the transaction response time rise. If I can, I might actually pause it, because I'd like to show you the difference between when it starts to slow and we're starting to be impacted by the throttling, but we're not actually getting errors, compared to when we are. But that's an aspirational goal. We might not actually get there. So we're now at 10,700 users. I suspect we're about 520 concurrent Lambdas at the moment. What I'll do is I will change this view in LoadRunner to show me the last 3 minutes. So I get a bit better, I get more samples. So the moment I start to see transaction response time rising, then I will pause the scheduler so that I can catch it in that slowed down state. That's really, I think, a best practice for doing performance engineering, is catching things as they're starting to degrade, so that we can actually see the beginning of the degradation process. Otherwise, getting cause and effect confused, it becomes a real problem. I think we might be starting to see slowdown now. This one has just started to raise up a little bit. So yep, I'll pause that. So we're at nearly 12,000 users, and we've got a substantial degradation started to occur. So we're now at, instead of being 170 millisecond response time for these calls, which is the authorized call, we're now at 250 milliseconds. So I'm expecting to see the concurrent Lambdas rise much more. In the next minute, they'll rise up again. Now that we've got that, we can go back to our X-ray view, and we might be starting to see the odd. Let's have a look here. We're looking for purple. Actually, the best way to find purple is to look in our throttling. Our throttling group. And yeah, we got some purple. There we go. Oops, I hit refresh, sorry. Quite a lot of throttling. Look at that. All right, so that's good to see. So the throttling is on the OIDC users table, which is contributed to by the authorized call in this case. So this is a view like a slice of only the data that's resulting in throttling. And we're having 84 requests per minute logged. And this is a representation of the samples, which means we're probably getting 84 per second of this actually occurring. So let's take this and let's click on Analyze Traces. So let's actually, what we can do is we can highlight these ones here, hit Analyze Traces, and we'll see that it's occurred in the last little time. We can scroll down. Now we can see that the only client ID is this one starting with FEQ. We're not getting a mix of clients, they're all from one client. That tells us it's to do with a client ID, which I reckon is pretty cool. Now if we click on one of these traces, we can see that the slowness is all in update item. So we're doing a get item, another get item, and a slow one on update item. And if we hover over here, we've got a remote fault caused by throttle exception. So throughput exceeds the current capacity of your table or index. It says it's auto scaling, but it's not in this case because it's to do with a hot what do you call it? Hot key, they call it, which is on a partition. So that's good to see. If we go back to our previous view and we go back to the service map and we look at everything, not just... Let's have a look at some other transactions while we're here. So if we look at authorize, for example, and let's have a look at Analyze Traces. So we've got 32,000 traces to look at. Now we've got 54.49% this one with client ID of FEQ, which is great because that's what I said we should get with that script. You can see the script works. Now if we look at one of these, we can sort them in response times. And let's choose one of these. So an authorized should be a couple hundred milliseconds. And we can see here in the service map that we've got the invocation, and we've got a get item, another get item for DynamoDB. Then we've got this walloping great slow update item, and then we've got the things that follow one after that. See this waterfall? This actually tells me that I really ought to refactor my code, because at the moment I'm doing a whole lot of sequential get items that are asynchronous and waiting for each other. I really could read the tags, AMR, scope, and other things concurrently. I don't really need to do them in sequence. I could knock off 30 or 40 milliseconds of response time by doing that. But that means nothing compared to waiting 1.4 seconds because of this OpenID Connect call to an update on the DynamoDB table that's in using a hotkey. So I think that's pretty cool. Let's go back now to the load test and let's have a look at how we're going. So we're at 940 concurrent Lambdas at the moment. So we haven't hit a problem where the slow response times have resulted in a breaching of our 1000 Lambda concurrent limit that's on my default AWS account. It's a default limit. If I was to resume the scheduler, then I'm going to blow that. So I'm going to do that so we can see what happens next. Resume scheduler, and then go back to here to the service map. And when I now refresh the service map, I'm going to start to see other errors coming up. So in this case, let's have a look at one of these errors. We can look at fault. We can just click on fault, analyze traces, and then we'll see all of the traces to do with this fault. Now this is affecting it's affecting everyone, not just the OpenID Connect client ID, which has got a hot partition. It's not telling us why, but I know the reason is I've exceeded my 1,000 limit. It'd be nice if I could show that to you. Oh, pending. Yes. Okay. So it says here that the invocation stage is pending. Usually what that means is it's waiting for a chance to be able to invoke this Lambda, but it can't because all the 1,000 Lambdas are running. So anyway, that's that. We're running at 13,000 users. I could let it go all the way to the 14,000, and then I will stop the test, and I'm going to do a bit of post-test analysis, and then I'll come back and join you for some more. But I think I've given you a pretty good run through of the way that X-Ray works. Let's have one more look at X-Ray before I stop the test. Service map. 1 minute. Refresh. Computing the map. Now we can see a much higher error rate over here, and we can see this little bit of purple, and this is the root cause of that error map. In fact, what I'll do, I will stop the test. I'm going to remove those extra 10 entries from the script so that I have even distribution, just to show you that at this level of load we won't get these errors if we remove the hotkey problem. So I will do that, so you can just join me again in a few moments. So I'm back. I've updated the script so that now the script is, both scripts are only using 10 evenly distributed client IDs. So let's go and have a look at the service map. You can see we haven't actually taken very long. You can see the time up here since last time. Now we shouldn't be having any errors, really. We certainly shouldn't be having any errors that are to do with throttling. It's a good sign. So this throttling group, so the throttling group itself, if we go up to oh, I don't know how to change a group. When you go into a group, you can create a group, and you can call it whatever you like, and you have a filter expression. You paste the filter expression in there, and the way you get that filter expression is when you're looking at the traces and you find something you want, you can just copy that filter expression from the service map, and then you can actually make that into effectively the basis of a group. You can tweak the numbers, which I reckon is pretty cool. Oh, sorry, default. So I'm expecting to see mostly green, which I'm seeing the odd person error. It's pretty small, but still seeing it. Push identity. Isn't this great though? The way that you can graphically see this DynamoDB table is being written to by, in this case, 1, 2, 3, 4 different functions, and like this token function is interacting with 6 tables. And if I want to look at common tables, I can go to the token one, and I can see what 2 API calls or what 2 Lambda calls are actually doing. Also, it's nice to see this invocation. So we've got about the same number coming from each, and sometimes they're lopsided. You don't see that. You might see 65 per second. Remember, we've got our 60-fold multiplier here per second from here, 2,500 per second from here, and so on. So that's good. And I'll show you now. Back to let's have a look at some of the nice way you can make use of. So let's have a look at this token here. So this token call has got 2 peaks in the response time. So we've got a peak that's a few milliseconds and a peak that's about 100. If we have a look at the peak that's about 100 and analyze traces, then it gives us a nice response time distribution showing us this of the selected set of the ones that we want to look at. We can now go and have a look, and we'll see a nice mix of client IDs, which is good. we can have a look at response times, and we can sort them. Let's choose the slowest one, and we can see that it took 256 milliseconds, and we can see the contributors to this in here. I don't know why we've got a gap there. Let's have a look at another one. So invoke, for some reason it's taking a while to release. Don't quite know what that is. Let's have a look at another one. This is what I'm expecting to see. I'm expecting that the sum of all of the component calls should be roughly equal to the total invocation time. There shouldn't be a lag at the end like those other ones. And the gap between here is internal processing. I think I showed you in a previous video that I've instrumented segments within some of my code that actually shows like the compute time. So in the authorize one, I've got that. Let's go back and do an authorize. Let's look at the authorize. Now in authorize, we've got a big response time around here. Let's have a look at the typical ones. Analyze traces. And we've got a nice distribution here of clients, which is good. And let's just randomly choose one. Now in here, we've got create keys. This was a special segment that I instrumented in the code. And you can see that's like 0, actually closer to 1 millisecond. And we've got another one over here, JWT crypto. It's actually where I do the signing of the whole payload of the claims and the header, so that I've got a cryptographic signature there for the JWT or the JOT. So you can see that takes 14 milliseconds at the moment. I have noticed that this amount of time, which is some simple CPU processing, varies from 10 to 30 milliseconds over some tests, which I don't quite understand, because if I've got the same amount of CPU allocated to a Lambda, I would have thought it would always be the same amount of time to do the same compute. Let's just look at another one randomly. So that took 9 milliseconds. Or maybe there's a bit of variety if there is extra scope information in there, but I wouldn't expect a threefold difference for a slightly different payload. Let's have a look now at how our test's going. There we go, 14,001 users. We're actually coping pretty well. We've got 700 concurrent Lambdas running, or maybe a bit over 700, but and our response times are under 200 milliseconds even for the authorize, which is pretty cool. So I think that's great. I'm going to let this run for another minute or so. We're at 4.6 million transactions. Gee, you really do a lot of transactions quick with this. And then in a subsequent video, I'll show you some of the analysis you can do post-test with LoadRunner, but also with X-Ray, so we can compare two periods of time, one where we had an issue and one where we didn't, so we can actually look at the statistical profile. So X-Ray is really awesome for what it lets you do. So it's great how, if we go back to the service map, last minute, it's great how even under all this workload, we get great visibility into what's going on from an end user perspective. So get saved user ID, we've got a small number of errors, we've got no purple, we've got a few failures over here with tokens. I'll dig into that separately, but we've got no purple. And to prove that, go back over to here, throttling, no purple. So there's no throttling taking place. So we might have occasionally bumped into 1,000 concurrent Lambdas, but we've got no throttling at the DynamoDB level causing it. So hope you found this useful. Next video, I'll dig into the post-test analysis and doing some clever things, and maybe even setting up some monitoring and alerting within X-Ray so that we can get alerted, and I'll fire off a test that fires off those alerts, which I think is a new whole level of doing application performance monitoring in conjunction with load testing as well. I look forward to the next video. See you later.